right, let's record on this computer. Okay, perfect. Okay, so today we're going to talk about cosets. Now, if you've looked at the reading guide, and hopefully you have, right? Hopefully you've done some of the reading ahead of time. You've seen that we're surprisingly not covering a lot this week. And the reason for that is, we're going to talk about cosets. Cosets are a fairly major topic, and they can be quite confusing because, in particular, even though it doesn't occur in this section, which I think is section 6, right? Even though it doesn't occur in this section, they're the main component of what's are later going to be quotient groups. And I think that for many students, this class might be their first real exposure to taking quotients, right? In some sense, you've done this before in Math 102, anytime that you look at the set of equivalence classes under an equivalence relation. But in this class, we're really going to work with quotients for the first time. And quotients are really tricky, I think, the first time you see them. Once you've played with them enough, you get a good intuition for how they work. Everything is very natural. But things are inherently difficult, I think, the first time that you see them. So we're basically, I think, taking this part slowly just to ease you into the idea of quotients before we actually hit them full bore, because once we have quotients, we really unlock a lot of really cool and really interesting stuff. And quotients are fundamental, right? So, I'm kind of getting ahead of myself a bit here because obviously we're not talking about quotients today, but just as kind of like something to think about in the future, for those of you who are just like, oh man, quotients are gross, I never want to see quotients again. If you go and you do any higher level of math, you're not going to be able to avoid them, right? Quotients show up everywhere. There's such a critical and important part of mathematics. Okay, so that's just something to think about. But let's, we're not there yet. We gotta set up a bit of the infrastructure. Now, let me tell you some stories. No, you know what? First, let's just define what a coset actually is so that we're okay with that. Let me make sure I can see my chat. Okay. Oh, I hate when that little back thing gets put in the middle of the screen. Okay. Whoa, what happened? All right, so we're talking about cosets, and the first thing we should do is be like, well, what the heck is a coset? So definition, right? If G is a group, and H is a subset, okay, so in this case, we're saying it doesn't have to be a subgroup. Now, 90% of the time that we talk about, 99% of the time that we talk about cosets, we're going to use a subgroup, but technically it doesn't have to be. And H is a subset. We define, okay, so there's a couple of definitions here. One, left cosets to be any set of the form AH. And what we mean by that is the collection of all AH time where H is in H. Okay, so A is some fixed element. Maybe I should say that, for some fixed A in G, right? So we fix an element A, and then we look at all the products A times H, where little h is allowed to cycle through big H. Okay, so that's the idea. And it's a left coset because A occurs on the left-hand side. And so, of course, dual to this, we'll have the notion of right cosets, where A occurs on the right-hand side. So again, this is to be any set of the form HA, all right, like that, for some fixed A in G. And that includes the identity, right? So we could totally use the identity here. And you can see generally, there's no expectation that these might be the same thing. Even if you have the same A and the same group, there's no expectation these will be the same thing. And we'll see via example later that, yeah, they're not in general. But obviously, if your group is abelian and the order of multiplication doesn't matter, in that case, yeah, left cosets and right cosets are exactly the same thing. And then a two-sided coset, and we don't use these in this most general form too often, to be any set of the form. And I'm going to Digress a little bit from what the book has here, but it's basically the same thing. But you can kind of see what the pattern is. Anywhere where you have big H appearing, you're just going to let that cycle through all the elements of little h, and you're going to make a set from all the products of that thing that you get, right? For fixed A and B in H, okay? So these are the notions of cosets, and your first instinct absolutely is probably, well, why the hell do we care, right? And again, there's actually a lot of reasons why we care. A lot of really important stuff comes from cosets, but it's probably not exactly clear yet. I'm going to hope that I can make or inspire you at least to be like, oh, okay, there's a very natural reason why we would define these things, but by the end of lecture, it's going to take a little bit of building up to get there. But I'm hoping that by the end, you'll be like, oh yeah, okay, that makes sense. Okay, that's the natural thing. Okay, so let's do an example of what sorts of cosets could we have. I'm going to just do a really simple example to start, and then I'll do something more complicated. So example, so consider, Z with addition, our standard, nice infinite cyclic abelian group. And we're going to take H here to be 3Z, right? And so notationally, these are just the multiples of 3, right? Why are A and G in the left and right coset definition A, B? Oh, it should be G. You're right. Thank you. Obviously, doesn't make sense to say H, but you are absolutely correct. Thank you. Okay, and 3Z here is just going to be basically like all the integer multiples of 3, right? And so this is just kind of a shorthand notation that we use for this. So this actually is a subgroup, right? It definitely has an identity. It's closed under addition. It's closed under inverses. This actually is a subgroup. But what we could say is, find all of the cosets for this, particular choice of H, right? Find all possible, I'm going to say left cosets. And of course, all the left cosets are exactly right cosets because Z is abelian, but let's not worry about that. And in particular, I don't care about two-sided cosets. Let's not worry about that, okay? And so basically, if we just kind of start writing stuff out, and this lecture, I think, is going to be particularly annoying just because we're going to actually have to compute some cosets. But let me tell you, as a mathematician who's done a decent amount of work with cosets in my life, not like a crazy amount, not like a true algebraist maybe, but like I have never, outside of like teaching it in your introductory course, I've never computed a coset in my life, right? But it's the sort of thing you should like do once or twice just to like really have it underneath or in your experience repertoire. Okay, so obviously one possible coset is just the set itself, right? Where you kind of multiply by the identity. So the first one. And out of curiosity, actually, a nice bonus thing you could do is while you're kind of like thinking about the lecture is try to anticipate how many cosets are there going to be? Are there infinitely many? Or are there 7? Try and think about what's going to happen. So the first one is E, or I guess that's just, 0 plus 3Z, right? Because 0 is the identity here, which is just 3Z. Okay. And then we're going to have 1, which is 1 plus 3Z. And so let me just kind of write out some representatives of that. Oops. ... -5, -2, 1, 4, 7, ... right? So i.e. all the numbers which are congruent to 1 mod 7, or mod 3, sorry. 2 plus 3Z. And you can imagine these are going to be all the numbers congruent to 2 mod 3. And that's it. Those are all of them, because after that, it starts to repeat, right? So, oops, I don't want to show you that yet. Right, so this is all of them. These are all the cosets, since after this, they repeat, right? So for example, if we had 3 plus 3z, so what have I done now? I've taken all the multiples of 3 and just added 3 to them. Well, I still just get all the multiples of 3, right? If I do that. And same thing, if I add 4 to 3z, I get all the things which are congruent to 4 mod 3, which is the same thing as the stuff that's congruent to 1 mod 3, right? So it just starts to repeat, and it doesn't become particularly interesting. So immediately there, we've completed all of the cosets. So we've got 0 plus 3z, which is just 3z itself, 1 plus 3z, and 2 plus 3z. And you can imagine that, yeah, this is going to work in general for any n, right? If I give you h being, 7z, then there are precisely 6 cosets, right? 0, 1, 2, 3, 4, 5, and 6, right? So that's kind of nice. And there's a couple of other points that I want to make here too. So as just kind of, let's say, a comment. So comment, right? Of the 3 cosets, note that they're all pairwise disjoint. These are all pairwise disjoint. Right? So what I mean by that is like 3z intersect 1 plus 3z is empty, right? And 3z intersect 2 plus 3z is empty, and so on. So that's what it means to be pairwise disjoint, right? Is that if you take any 2 of them, then they're all disjoint, right? Should I just write them all out? I guess there's only one more, right? Which is 1 plus 3z intersect 2 plus 3z, right? So none of them have the same number of elements. And in particular, again, that's in some sense obvious because we said, oh, look, they're the numbers which are congruent to 0 mod 3, 1 mod 3, and 2 mod 3. We know none of those are the same, right? And also, they union to give you all of z. Now, does anyone remember, what do you call such a thing? If I give you a collection of sets that are all pairwise disjoint and they union to give you everything, what do you call that? Does anyone remember? So I give you a collection of sets which their union is everything and no 2 of them overlap. No one remembers? Some stat term. Well, first of all, I'm offended that you think it's a stats term. Okay, it's totally a math term. And maybe if the stats, if the stats people borrowed it, well, they borrowed it from us, not the other way around. No, okay, so like that's a partition. Do you remember doing that? When you were, maybe in 102, you probably would have seen it. Like you learned that the equivalence classes partition your space, right? So no 2 equivalence classes overlap and every single element is in some equivalence class. Does that sound kind of familiar to you? Right? So partition is you take a space and you kind of like cut it up into pieces. Those pieces don't overlap each other because you cut them up and everything is in some piece, right? So it's a partition of your space, right? So this is going to be interesting. And I'm going to highlight this kind of as we go to really kind of point out like, yeah, cosets partition your space, at least the distinct cosets partition your space. Okay, so that's kind of a nice thing. All right, so let's do now a non-abelian example. And I'm going to give you a shot to do this because like I said, you should compute cosets at least once in your life. Okay, so I'll end up giving you a couple of minutes to do this. But okay, so true story. So I was on the subway yesterday and I'm coming back from like hockey or going to hockey, whichever one, I don't remember. And I'm prepping my lectures for today. And I'm like, okay, what's the first non-trivial, like non-abelian example where we can compute cosets in? And I constructed these examples of what we were going to do. And it turns out I then went, and I swear I hadn't looked at Ali's lecture notes or his lecture slides. And then this morning when he kind of canceled his lecture, I looked at his lecture slides just to make sure I would kind of like cover very similar things. And I realized we came up with exactly the same examples. I am going to diverge from him eventually, but like this example is actually pretty close. Right, and I usually try and, for those of you who are maybe watching me for the first time, the reason I usually try and diverge is so that if you watch his video and you watch my video, you get a different set of examples, right? But so this one is pretty close. So consider, let's say S3, right? So the symmetric group on 3 elements, it's our smallest non-abelian group. And H, I think I was slightly different from him in that I chose a different transposition. Which one did I choose? I just chose 1, 2, right? So again, this is actually a subgroup, right? It's not just a set, it's actually a subgroup because the element 1, 2 has order 2. And so, yeah, this thing is closed under inverses and multiplication and everything like that. So find all the left and right cosets of S3, okay? And the point here isn't just to make your lives terrible because you actually have to compute this, and it doesn't take too long, but it is a bit of a slog. But there's actually a teaching point here that we need the cosets of H here in front of us so that we can kind of make some of these points, okay? Now, when I was on the subway yesterday, I did this problem without this, the Cayley table, and well, actually what I did is I just reconstructed the Cayley table from scratch because it's much easier if you can actually see what the elements are. Maybe let me make the Cayley table a little bit bigger. Okay, and just as a reminder, the top elements will be the rightmost elements. And the columns are the left elements, right? So if I wanted to do, for example, 1, 2, 1, 2, 3, I would look up the 1, 2, 3 column and then the 1, 2 row. So that would be this element right here. Okay, it's just in case you've forgotten when you're looking at a Cayley table, like what the order is, right? You're going to look at the right element is the column and the left element is the row. Okay, and last time before I made my table bigger, I just included this little line to remind you where the headings were. Okay. All right, so I want you to try this. I'm going to give you about 5 minutes just to plug them out. There are 6 things you have to compute, right? 1 for every element of the group. 1 of them is dumb. 1 of them is E times H. So that's just H itself. So really there's 5 things you have to compute for the left cosets. There's 5 things you have to compute for the right cosets. Like I said, I'm going to give you 5 minutes or so and just see if you can grind them all out. And then after that, I won't make you compute any cosets again, and I'll compute all the cosets for you. Okay, but let's just try this. And like I said, 5 minutes here. And if you have any questions, don't hesitate to throw them in the chat and I will answer. And I'm going to pause the recording. Somebody please remind me to unpause it. Okay, so it's been 5 minutes now. And I'm not going to waste time writing all these out because I already computed them ahead of time. So I'm just going to, sorry if that's a little bit loud, I'm just going to pull them up here. Whoop. And up further like this. Right, there we go. There they all are. So like I said, I computed these ahead of time. And yeah, it's a little bit, it's a little bit of a slog. It's not too bad though, because in some case, right, like one of the elements is the identity. So every time you just multiply that in, you know what it is. So really all you're doing is checking the multiplication table a whole bunch of times. Okay, so let's just ignore the right cosets for now. Hopefully you got something similar, but let's take a look first of all at the left cosets. And what we'll notice is that there are a lot of cosets that are the same here, right? So for example, these 2 cosets here, these are the same. I think these 2 cosets, yeah, these are the same. And then these 2 cosets are the same, right? So there's actually only 3 unique sets of cosets when we do this. So there are only only 3 cosets, right? Because just like our example with Z above, some of them start to repeat, right? So we can take as being our cosets H 1, 3H and 2, 3H, right? Or if you wanted, you could, of course, have taken 1, 2, 3H and 1, 3, 2H. Those are the same, but there are really only these 3 cosets. And again, as I kind of said above, notice that they don't share any elements in common. So they're pairwise disjoint. And again, they union to give you everything. So once again, these are pairwise disjoint. And their union is all of S3, right? Do you see that that's true, right? 1, 3H, 2, 3H, and the identity H, they all have different elements inside of them. And every single element of S3 is represented in one of these cosets, right? So that's kind of an interesting point. Now, before I talk about the other interesting thing that we can see, why is this important? Can anyone guess why there are exactly 3 cosets? Or maybe, you know what, maybe let's come to this. If you know the answer, that's great. You can put it in the chat. Maybe the answer will be more clear when we do our next example. But yeah, think about that. Like, is there any way I could have known that there would be exactly 3 cosets, right? Like how would I have been able to come up with that? Okay, so I want you to think about that. Now, the other thing to notice, I guess there's a couple more things to notice, really. So here, let's say comment. Okay, so generally, these are not subgroups, right? So 1, AH is generally not a subgroup, right? Most of them don't even have the identity element in it, right? And if you're a subgroup, you have to have the identity. So 4, let me say 2 of the 3 aren't subgroups, right? So immediately make sure that you're not, even though H is a subgroup, AH does not need to be a subgroup, okay? So you don't want to make that mistake because that's a pretty common one. Number 2 is that AH can be equal to BH, even though A is not equal to B. Right? So in the above example, we had that 1, 3H was the same as 1, 2, 3H. Right? Even though 1, 3 and 1, 2, 3 aren't the same. However, what you might notice is that 1, 3H has the cycle 1, 2, 3 in it, right? This is an important point. The cycles that are the same, all like the element which generates the coset is in that coset, right? So look at let's look at 2, 3H. What are the elements of that coset? Well, they're 2, 3 and 1, 3, 2. Well, interestingly, if we look at 1, 3, 2H, that's the same coset, right? So there seems to be this thing that if cosets share an element, then they end up being the same coset, right? And 3, what was the third comment here that we wanted to make? Let me just pull up my notes. What was the third case? Oh, yeah. And now if you look across the aisle, AH is generally not equal to HA, right? So if we take a look at this, these are not the same, right? And of course, that's going to happen. Like we needed a non-commutative example for this to be true. I mean, they're pretty close, right? They both have the element 1, 3, but then the left-hand side has the element 1, 2, 3, and the element on the right-hand side is 1, 3, 2, right? So left cosets generally aren't going to be equal to right cosets. They are if your group is abelian, but generally this isn't true, right? Okay, so are there any questions about that? Okay. All right, good. So again, to me, these things are all like very, very clear because I don't think about cosets this way. And I'm going to try and show you how I think about cosets just to make things maybe a little bit more clear. But we have to, like I said, we got to build up to it, okay? So let's do some more building. So exercise. So again, we're going to take S3. I'm not going to make you do this one. Let S3 be the group. And let's take K to be the cyclic subgroup generated by 1, 2, 3, or equivalently 1, 3, 2. All right, find all the left and right cosets. Of K. Okay, and again, I'm not going to make you do this, but you imagine you go through and you do exactly the same set of work. And if you did this, what would you get? Well, you would get this. All right, so let me just write solution here. So I worked these out ahead of time so that you didn't have to. Because it's just a slog, right? It's just a lot of work. Okay, and there they are. Okay, so you can work them out. And one of the things that we note in this case, interestingly, is in this case, AH is equal to HA. Right? So that's the first thing. The other thing is there are only two distinct sets of cosets. Right? There's K, and then there's 1, 2K. That's it. Those are the only two distinct K sets or cosets. Everything else is just a repeat of one of those two things. Okay, does that make sense? And again, notice that the fact that 1, 2K, 1, 3K, and 2, 3K are all the same because 1, 2, 1, 3, and 2, 3 all appear in the coset, right? These cosets are all the same because those are precisely the elements which occur in those cosets. If two, this, you know, we're kind of building up to this idea that if two cosets share an element, they have to be the same coset, right? And again, that's very much like equivalence classes, right? If two equivalence classes, if I say here are two equivalence classes, and there's this thing which is in both of them, then these equivalence classes actually have to be the same thing, right? Now, my question to you is, on the basis of what we had above, right? So up here, when I had H was a 2-element set, I had 3 cosets, right? H, 1, 3H, and 2, 3H. Now, if I let K be this subgroup, right, which have 3 elements in it, I only had 2 distinct cosets. So can anyone tell me what they think is going on here? Like, and again, notice that the 2 distinct cosets, these are pairwise disjoint and they union to everything. Pairwise disjoint and union to everything. Right? So what's going on there? So let's say, for example, I gave you a group of group of order 12, right? So it's got 12 things in it. And I gave you a subgroup of order 4. How many cosets would you guess that there were? Okay. The group has 12 things. The subgroup has 4 things. How many cosets do you figure there are? Nobody's even got a guess? This is super, yeah, it's 3, right? It's going to be 3 because, again, we know that it's a partition of, like, so far, again, we haven't proven this, but the idea here is that the cosets seem to be partitioning up our space, right? In the sense that I've got 12 elements and I'm cutting it into blocks where each block has 4 things in it. Well, how many blocks am I going to have total? I'm going to have 12 divided by 4 equals 3 blocks, right? So if this idea ends up being true, if the fact that cosets actually form a partition of my space, then I'm always able to count exactly how many cosets I'm going to have because, again, as long as I use a group, because then I'm going to take the total size of my group divide it by the size of the subgroup, and that will tell me how many cosets there are. But it also says something else super important, which is what we're going to talk about next week, which is therefore that the size of the subgroup, in order for this to be true, the size of the subgroup has to divide the size of the group. Does that make sense? Because otherwise you couldn't partition it. You couldn't break things into even parts, right? And this is going to be called Lagrange's theorem, which I think a lot of people have felt is true throughout the course, right? That the order of a subgroup had to divide the order of the group, but that's basically where this is going. If you know that the cosets form a partition of your space, then that says, well, your subgroup, the order of your subgroup had to perfectly divide the order of your group. Okay, and that's basically the proof, in fact, is to show that it's a partition. Okay, now the other kind of thing worth pointing out here is that, okay, we can't say anything about whether the left and right cosets are equal, right? Because up here, when H was this set, right, the cyclic subgroup generated by 1, 2, the left and right coset generated by 1, 3 was generally not the same, right? They were different cosets. And then I come down here, still the same ambient group, right? I'm still working in S3. But now I change which subgroup I'm using to generate my cosets, and suddenly now left and right cosets are equal. So you don't know anything, right? Because it depends on the ambient group, it depends on the subgroup you choose. You can't say anything about whether left and right cosets are going to end up being the same. And that's kind of sad. You would like to be able to hope that maybe some special property of the group would give you an idea of what you were doing, but unfortunately it just doesn't work that way, right? So that's kind of an important lesson. Sometimes they are equal, sometimes they're not. Generally, you have no idea, right? Unless you know something more about what's going on, there's really very little that you can say here. Okay, so does that make sense? Any questions about that? Okay, I promise this is the last time we'll compute subgroups. I mean, you could, on an assignment or a test be something asked to compute subgroups, but generally I don't care. I don't want to compute subgroups. What a mess. Or cosets, rather. Okay. All right. So the next thing is this collection of properties here. Let me just bring them up so that they're on the screen. And maybe I'll make them a little bit bigger so we can see them. Okay. And so, this is just a copy of paste of this proposition that's in the book. And okay, so there's these 9 properties here, and you're like, oh man, there's no way I'm going to remember 9 of these things. Especially, you can imagine if you're asked to do any proving about things with cosets, any one of these properties could come in, and you're just like, oh, this is an overwhelming amount of information for me to try and remember. Like, how am I supposed to get a good intuition for this? Again, I am going to make it so that almost by the end of this lecture, almost all of these will be obvious. And I mean obvious, it depends on you remembering something from Math 102. But if you remember that thing from Math 102, which in theory you should, right? You are technically, we are allowed to ask that you know those things. But if you remember something from 102, then 1 through 7 are trivial. They're obviously true, right? You don't have to prove them because you prove them in 102. All right, so we'll get to that. But there is some utility and there is some value in actually going through some of these proofs. Now, the book does have all of the proofs of these facts inside of it. I mean, it only does it for left cosets, but the proof for right cosets is identical. I think there are a couple of ones that are really nice to highlight, and we'll do ourselves right here, right now. But this is a really good opportunity for you to practice with cosets as well. So if you're just like, hey, I want to practice them, don't look at the book, right? Don't look at its solutions, and just go through 1 through 9 and make sure you can prove every single one of these. None of them are tricky. None of them are hard. You should be able to do every single one of these, right? As sort of like a base litmus test of, do I understand cosets, right? So when you're thinking ahead to the next quiz and you want to make sure that you understand stuff, this is a great place you can do it. Now, the ones that I want to prove 2, because this one's nice and important, right? And 2 is very, closely related to 4, but it says, AH, the coset generated by A, is just the identity coset if and only if A was in H to begin with, right? So a lot of these also, something of value would be to look at these and try and translate them to English, right? So I feel like this one maybe is a little bit hard to read, especially since it has the right cosets in it, right? But AH equals H if, and I think it's actually worthwhile writing if and only if here. A is an H, right? And yeah, that is what it says, but like let's kind of ignore the right coset thing for now. I think that's kind of just muddling the point. So the coset generated by A is the identity coset if and only if A was in H to begin with, and we saw that, right? So right here, we saw these facts were true. Oops. So this one, this coset, and these two cosets were the same precisely because 1, 2, 3 and 1, 3, 2 were already in K, right? And I guess I should point out too, an assumption of proposition 6.3 is precisely that it is a subgroup now. Okay, we're not taking an arbitrary set. We're really saying H is a subgroup, right? Otherwise, these theorems aren't true. Okay, so if and this makes computing a lot of your cosets very, very quickly. You just look at all the elements which are in the coset. You're like, boom, these are all the identity. Okay. The other one I want to prove is 5. Okay. And 5 again basically says that it forms a partition over space. Either two cosets are equal or they're pairwise disjoint, right? So two cosets are either equal or disjoint. There's nothing in between. Okay, you don't intersect your cosets in some smaller set, right? Like the Venn diagram is either the circles don't touch at all, or they perfectly overlap each other, right? Those are the only two possible outcomes. That's what 5 says. They perfectly overlap or they don't touch each other at all. And then 6, because 6 is the thing which tells you when two cosets are equal. 4 also gives us a bit too, but 2, 5, and 6 are really the ideas here. Now, again, it almost feels wasteful for us to kind of like talk about these proofs just because I'm going to give you a better reason why 1 and 7 are all identical very, very shortly. But again, I think it is kind of worth going through and just, doing some proofs every now and then just to make sure that you're very comfortable with the material. So let's try this. So let's do proof. So like I said, I'm going to prove 2, 5, and 6. Okay, so for the proof of 2, we've got an if and only if statement, right? So let's prove the forward direction first. So let's suppose that AH equals H and show that A is in H, right? Okay, and in this one, what we note is because H is a subgroup, it has the identity element, right? So since H is a subgroup of G, then E is in G, or sorry, E is in H. So A is equal to AE, right? And that's in AH, right? Because E is in H. But AH is equal to H, and so we're done, right? We've shown that A is in H. Okay, and in the opposite direction, what are we going to assume? We're going to assume that A is in H. And let's show that AH is equal to H, which means we have to do a double subset equality, right? So let's do this direction first. This direction is trivial. Since A is in H and H is a group, right? It's a subgroup, but in particular, subgroups are also groups. That means it's closed under its binary operation, right? So whenever I compute AH, that's A times an element of the group, but A is in H as well. So that automatically tells us that every single element in AH is also in H, right? Because the binary operator is closed. And if I do the opposite direction, okay, so I want to show that H is a subset of AH. So we're going to say let H be in H, so that A inverse H is in H, right? And you might have to think about that one a second, but since A is in H, its inverse is also in H because H is a subgroup. So if I multiply those two elements together, again, binary operator is closed, so A inverse is in H as well. And that means that that H is equal to A times A inverse H. At this thing here is in H, so this is in AH. Which gives us the opposite inclusion, right? Okay. Any questions about that part? And again, there's going to be a sense in which this is like obviously trivial if you know the right way of thinking about it. And again, I don't remember these like 7 properties because this isn't how I think about cosets. But so I'm going to give you a better way of doing that in a second. Okay, 5. Let's think about what 5 is, right? Let's just go up and remind ourselves. So 5 says 2 cosets are either equal or they're completely disjoint, right? The Venn diagrams either overlap or are separate. All right, so we know that they can be disjoint, right? We just did a whole bunch of examples. We did 3 examples where we computed cosets and showed that they were disjoint. So what we want to show is that if they're not disjoint, they have to be the same, right? So suppose that AH intersect BH is not empty, right? So in particular, there's something in the intersection. So fix some X in the intersection and choose. Now, this is an important part. Here's a very common mistake that students make. I know that X is in AH and X is in BH, right? Maybe let me say that first. So fix some X in AH, intersect BH, so that X is in both AH and X is in BH, right? So now I'm going to say choose H1 and H2 in H so that X is equal to AH1 is equal to BH2. They are different H's, right? Very common mistake at this point is for a student to say, oh, look, it's in AH and BH, so there exists an H where X is equal to AH and equal to BH. That's not true, okay? They're generally can and will come from different H's. So make sure that you choose 2 different H's when you do something like this, okay? So it's equal to AH1 and BH2. And let me just double check my notes here. What did I want to say? Oh, right. Yeah. Okay. So now here we're actually going to use property 4. So we have to go back up. We have to look at what property 4 says. So property 4 says that if A is in BH, then the cosets are equal, right? So it says that if an element of if A is in BH, then the coset generated by A is the same as the coset generated by B. Well, that means since X is in AH, actually, maybe I didn't need this. Let me see. So since X is in AH, that means that X, oh yeah, I didn't need it, right? XH is equal to AH, right? And since X is in BH, the coset generated by X is the same as the coset generated by B, and thus AH is equal to BH, okay? So this here uses 4. So you have to prove that if you really want a full understanding of this, but that's fine, right? It's a little exercise for you. But again, I'm going to show you a way in a second where you don't have to think about any of this. And then finally, number 6 is the most important, and it's most important for, I think it's the most important property of all of the 9 listed there, which tells you precisely when, like a criteria for determining when two cosets are equal, right? So it's the statement that AH equals BH if and only if A inverse B is in H. And of course, this relationship is completely symmetric. So instead of doing A inverse B, we could have done B inverse A, right? And that would have been exactly the same thing. An important note here that I really want to point out, though, so comment, not A B inverse. Okay, the inverse has to be on the leftmost element when we're talking about left cosets. If you put the inverse on the right, you're talking about right cosets. And this is relatively easy to remember because if you look at this equation right here, and you were to say, okay, I want to put like the A on the other side, what would you do? You'd kind of multiply both sides by A inverse, and you'd get that H is equal to A inverse B, right? So the inverse is on the left. Same sort of thing. If you wanted to get the B on the other side, you'd multiply both sides by B inverse on the left, right? When you're dealing with right cosets, you'd multiply by the inverse on the right. So make sure that you're keeping track of which side the inverse comes on, because otherwise, if you put the inverse on the wrong side, not only is it going to be wrong, but nothing is going to make sense. Okay, so the inverse occurs on the left element, and that's because we're dealing with left cosets. Okay, left inverse, left cosets. And yeah, this proof is actually, we'll break after this proof, but there's again a bunch to prove here because we've got an if and only if, and we've also going to have to do a double subset inequality, right? So let's do the forward direction first. So suppose that these two things are equal. This is actually the easy direction. And then let's show, remember, what are we trying to show? So we want to show that A inverse B is in H. Okay, so let's pick H1 and H2. Again, different H's, so that A H1 is equal to B H2, right? These two sets are equal. So basically what I'm going to say is going to choose an element in this set. Because it's an AH, I can write it as AH1. Because it's an element of BH, I can write it as BH2. And those two things have to be equal, right? And now what I'm going to do is I'm going to solve for A inverse B. And if I do that, what am I going to get? So I'm going to get A inverse B is going to be equal to H1, H2 inverse. If I did this correctly, let me double check. So multiply both sides by A inverse. And then to get rid of H2, I'm going to multiply on the right. But yeah, that's right. And this is an H, right? Because H is a subgroup. And again, we're seeing how important it is in every single one of these proofs that we've assumed that H is a subgroup, right? That it's not just an arbitrary set, that it really is a subgroup. Okay, that's what we wanted to show, right? That's what we said we wanted to show. Now, the opposite direction isn't too much worse. It's just that it has a double subset inequality, but it's not too bad, right? So suppose that A B inverse is in H, and we're going to show that these sets are equal. And before I do anything, let's write out the following. So since A inverse B is in H, there exists some little h such that A inverse B is equal to H, right? That's what it means, that it's in the set H. It's equal to some element of it. Oops, sorry, little h, not a big one. And this equivalently means that what? So B is equal to AH, or if I were to solve for A is BH inverse. And the critical part of this is that notice that in both of these cases, when I've written A and B, whatever the H is, or the H inverse, who cares, but it's on the right, right? It's the right of the element. So I've got B is equal to A, then H, and A is equal to B, then H inverse. So the fact that H inverse is on the right there is critically important, and you would not get this if you reversed whether it was A that had the inverse or B that had the inverse, okay? So this is important, and let's see why. So to do one inequality, let's say we go in this direction. So I want to show that AH is a subset of BH. So we're going to say let AH1 be an element of AH. Okay, so thus, if I now substitute this line into here, so I'm going to get AH1 is equal to BH inverse H1. Again, this thing is in H, so this whole thing is in BH, and that tells us we get one inequality. And again, you can imagine how the other direction goes. Let AH2 be in BH. Again, different H's, right? Don't make that mistake, choosing same H's. Or sorry, B, obviously that should be B. Thus BH2. Now I'm going to substitute my other equation in. So I'm going to get AH2. This thing is in H, again, because it's a subgroup. So that's an AH. And that gives us the other inequality, like so. Okay. So this is just like 3 of those 9. They're all roughly the same length. And hopefully what you see here, maybe let me zoom out a bit. Hopefully what you see is that like none of these proofs is too bad. Like as a general rule, you didn't have to do anything tricky. They're not terribly long. The proof technique is the standard thing, right? If it's an if and only if, you're not doing any contrapositives, you're proving them directly. When you want to show 2 sets are equal, you're doing a double subset inequality. As a general rule, these are all really good examples of relatively simple proofs to get your feet wet and make sure that you're comfortable with cosets. Okay, so that's I really can't emphasize this enough. Even if me going through these proofs, because I went through them, I think relatively quickly, right? I blew through this in like 8 minutes or so. Sometimes when you see someone else do a proof, you're just like, whoa, what the hell happened? Especially with algebra, because there isn't a lot of like geometric intuition happening. So it's possible that you just watched me and you were just like, I have no idea what happened. And that's okay. Like you take a second and maybe during the break, try and redo these proofs and then compare them to what's on the screen. I'll keep this zoomed out like this so that you can take a look at that. And then you can compare what you did compared to what I did. And so there might be a sense in which actually, if you didn't understand, that's better because it gives you an opportunity to try that from scratch, right? So yeah, like I said, I'll leave them up on the screen and then you can give them an opportunity or a chance during the break yourself. But otherwise, I think that I'll stop there. We'll take a 10-minute break. And then when we come back, I will then show you how, and I will come back to the screen. I'm going to show you that all of these results here, pretty much all of them, are just obvious, like are super, super obvious. So they're not worth remembering, right? Because if you understand how to think about cosets, they're all quote unquote obvious, right? So that's my goal. That's what I'm going to do for you when we come back. But until then, why don't we take a little break, a little 10-minute break, and then I'll show you that. Okay. So I have about 2:08, 2:09 by my clock. So 10 minutes is 2:19 Eastern. Otherwise, just time 10 minutes. Yeah, I'll show you that cool stuff when we come back. Okay. So I will see you then. And I'll pause the recording. Okay, we're back. And hopefully if you did try some of these things on your own, they weren't too hard. I don't know, maybe they were. Didn't seem to be many questions though, so I will assume it wasn't too bad. So now I'm going to diverge a little bit. And in particular, I'm going to show you something that isn't in the book. And I think that this is a very valuable perspective. I've been kind of hinting all along, not even hinting, I've been explicitly saying that this is not how I think about cosets. There's nothing wrong with this perspective. And in fact, I think you often want to have multiple perspectives of an idea, of a definition of a concept, whatever the case might be, so that you can use it to approach things in different ways. So the thing that I'm about to show you might take a little bit to digest. I don't think it's terribly hard, but again, it's going to really rely on your understanding of equivalence relations. And if you have a good understanding of equivalence relations, then it makes understanding cosets and how cosets operate much, much easier. Okay. Now, if you don't have a great understanding, that's fine. It won't be necessary to understanding cosets. I mean, it kind of will be. Like we're going to bank on this stuff in a couple of weeks a lot when we use quotients. So I'd say you probably want to have a decent understanding of this sort of material, but it's not immediately necessary, but it will be within the next couple of weeks, right? So this is worthwhile to take a look at and make sure that you're comfortable with, even in the relatively short run, okay? So like I said, this has something to do with equivalence relations. But what does it have to do with equivalence relations? So what I want to do is I'm going to state a couple of propositions for you, and then I'm going to tell you the implications of those propositions. I'm going to prove those propositions too. The propositions are very easy. Okay, so proposition numero uno is the following. So proposition okay, so if, let me just make sure I get the right one I want. If squiggle is an equivalence relation, on G, and remember G is a set, right? And as we learned in 102, you can put equivalence relations on sets, like that's totally fine. So right now we've just got an equivalence relation on G as a set. We are not using any group theoretic properties here. If it's an equivalence relation on G such that if A is related to B, now we're going to use the group properties. We're going to say this is an equivalence relation which respects somehow, is compatible with the group operation. So if A is related to B, then G of A is related to G of B for any G in G. Then two things. One, maybe I should number them. One, the equivalence class of the identity, which I'm going to call H, is a subgroup of G. And two, what's the second one? A is related to B if and only if A inverse B is in H. And I'm going to add, we're not going to prove this last part because we've already proven it. This is equivalent to saying the cosets of AH and BH are the same, right? So we know that if A inverse B is in H, then AH and BH define the same coset. Now, an important point here is to remember what is H, okay? H is not specified at the beginning of the problem. H is the equivalence class of the identity. So let's step back. I've given you a group. I've given you an equivalence class in the group, which satisfies a very special property that if A is related to B, G of A is related to G of B. Then I'm going to use the equivalence class of the identity to define H. Okay, that's one of the things that we're going to prove is the equivalence class of the identity is a subgroup. And then using that subgroup, that guarantees that the left cosets of A and B are the same, precisely if they're related. Okay, so we're going to prove this proposition. Okay, so for number one, immediately, obviously, E is in the identity, right? It's in its own equivalence class, right? You take the equivalence class of the identity, obviously, E is in there. Okay, so in particular, H is not empty. Okay, and then, so we'll say let A and B be elements of H. So from now on, I'm just going to call it H, but keep in mind, H is the equivalence class of the identity. So if A and B are in H, then what that means is that A is related to E, and E, well, let's say, and B is related to E, right? Since they're both in the equivalence class of the identity, but then by transitivity, A is related to B. So A is related to B. And then we could have gone straight there. They're both in the same equivalence class, right? They're both in the equivalence class of the identity, so they must be related to one another. Now, by the special property of the equivalence relation, right? If A is related to B, then GA is related to GB. For any G, what I'm going to do is I'm going to multiply both sides of this equation, of this relation, with A inverse. So let's say multiplying by A inverse, we get that the identity is similar to A inverse B, which means that A inverse B is in the equivalence class of the identity. And that's precisely the subgroup criterion, right? I started with an arbitrary A and B. I showed that A inverse B was in the thing as well, and therefore it's a subgroup. So we're done. Okay, and number 2 is almost identical. So, well, here, let's just do it. So we're going to assume, actually, we might be able to just do both directions at once. So let's assume that A is related to B, so that as above, right? From above, we've already shown that E is related to A inverse B, right? And this is actually if and only if. Right? So we have A is related to B if and only if E is related to A inverse B. And yeah, that gives us the result, right? So if and only if A inverse B is in the equivalence class of the identity. Okay, so that's it, we're done. Proof was very simple, right? Very straightforward. And it just, again, comes down to this special fact of the equivalence relation, that it kind of preserves, that it respects the group operation, right? So once you have that, boom, you're in good straits. Now, what we're going to do is we're going to prove basically the converse of this proposition as well. We're going to prove that every subgroup induces an equivalence relation, which has this special relationship. Okay, so we're going to prove that mirror proposition now. It's basically a converse of the above proposition. So we're going to say if G is a group, and H is a subgroup, and again, this is important that it is actually a subgroup, because we are going to use, right? Basically, what are the 3 properties of subgroup? It contains the identity, close under multiplication, close under inversion, right? Those are the 3 properties. We're going to use all 3 of those properties for this proof. So if G is a group and H is a subgroup of G, then a relation defined as saying A is related to B if A inverse B is in H is an equivalence relation that satisfies that special relationship that we had above, that if A is similar to B, then GA is similar to G of B for all G and G. Okay, so there's 2 things we have to prove here. We have to prove that it's an equivalence relation, and we also have to prove this special property, right? That A is related to B implies that G of A is related to G of B. And something really cool happens here. So there are exactly 3 properties of being an equivalence relation, and hopefully you remember what they are. It's reflexive, symmetric, and transitive, right? So let's see how those come in. So let's prove reflexive first, right? So here we want to show that A is related to A. So we fix some A in G and note that A inverse A is equal to the identity, but H is a subgroup. So yeah, that's in H. Thus, A is related to A, right? Okay, symmetric. So suppose A is related to B, right? Remember, symmetry means we want to show the opposite is true. We want to show B is related to A. So by assumption, though, if A is related to B, that tells me that A inverse B is in H. But H is a subgroup, right? So it's closed under inverses. Is closed under inverses, right? So if I give you an element of H, its inverse is also in there. So A inverse B inverse is equal to B inverse A is also an element of H, and that's precisely what it means for B to be related to A. Right? Okay, so this is cool so far, right? Again, the three real important properties of being a subgroup: you have the identity, you're closed under inverses, and you're closed under multiplication. So reflexive use the fact you had the identity. Symmetric use the fact you were closed under inverses. Can you guess which property is going to be important for transitivity? Yeah, it's going to be exactly that you're closed under multiplication, right? So for transitivity, right, we're going to suppose A is similar to B and B is similar to C, right? And then we want to show that A is therefore similar to C, right? That it passes through B. So by assumption, that tells us A inverse B is in H and that B inverse C is in H. Okay, so to show that A is related to C, we need to show that this is in H, right? That's what it means to be in the equivalence relation. So I want to show that that's in there. And again, if you look at the only two pieces of information I have, I need the B to magically show up. So I'm going to add and multiply by B and B inverse. This is in H. This is also in H. And since H is a group, it's closed under multiplication. Voila, right? If you ignore that middle bit, what have I shown? A inverse C is in H. So A is related to C. So every single important property of being a subgroup showed up in this proof, right? In exactly the ways that we needed them. So I think that's like pretty cool, right? That all of those things show up exactly the way you want. Okay, so thus, this is an equivalence relation. Right? And so all we need to show now is that special property. If A is related to B, then G of A is related to G of B for any G, right? So now suppose that A is related to B, right? So this means A inverse B is in H. And fix some G and G, right? So we want to show that GA is related to G of B. So to show that G of A is related to G of B, what do we need to do? So we need to look at GA inverse GB, right? We need to show that this thing is in H. That's what it means for these two things to be in or to be related to one another, is that the left thing inverted times the right thing is in H. And hopefully you see what's going to happen here. If I expand this out, the G and the G inverse just cancel each other out. I get A inverse B, but by assumption, I knew A inverse B was in H, right? So again, if you only look at the very beginning and then at the very end, this tells you exactly what we wanted, right? I think that's pretty cool. Okay, so what the hell was the point of doing all of this, right? Let's maybe look at the two propositions. So proposition, the first one says, the one at the top of the screen, says if I, let's call these special equivalence relations, right? Just so I don't have to keep repeating what the special property is. The special property being A related to B implies GA is related to G of B. So proposition one says, if you give me a special relation, then there is a subgroup such that the cosets are equal, right? And the second proposition says that if you give me any subgroup, it defines an equivalence relation via its cosets, right? I mean, we didn't explicitly talk about cosets here, but like this is the coset condition, right? This is precisely what it means for AH to be equal to BH, right? That was property number 6 that we proved above. So maybe let's restate this in a different way. Proposition 1 says if you give me a special equivalence relation, then that defines a subset on which cosets are precisely the equivalence classes. The second proposition says if you give me a subgroup, its cosets are equivalence classes of a relationship, of a special equivalence relation. Okay, so what this means, what we've proven here, so we've shown that there is a bijective correspondence between equivalence relations, or as we've been calling them, these special equivalence relations, and subgroups of G. And in this case, the cosets are precisely the equivalence classes. Okay, and that's possibly the most important line. The cosets are the equivalence classes. Okay, so every subgroup defines a special equivalence relation, and the cosets are the equivalence classes. And every special equivalence relation, there you can find a subgroup such that the cosets are the equivalence classes. Okay, that tells us there's a bijective correspondence between special equivalence relations and subgroups, and in both of those cases, the cosets are the equivalence classes. Okay, now if you understand this, that the cosets are always an equivalence class, I claim that all of these properties way back up here, I'm sorry, I know I'm going to jump. We've got a lot to go. All of these properties are trivial. Okay, maybe not 8 or 9 because they're not directly kind of statements about that. But here, maybe let me copy and paste this down here. Sorry, I know I'm moving around a lot. Hopefully that's not kind of bugging you too much. Yes, paste, please. Thank you. So now if we look at this, so of the following properties, all of 1 through 7 are just consequences of equivalence relations. Okay. So what does this say? Let's take a look at the fact that this is true. This says that A is in the equivalence class of A. Yeah, obviously, right? A is in its own equivalence class. That's not crazy. What does this say? This says that A is in the equivalence class, or sorry, that the equivalence class of A is equal to the equivalence class of the identity if and only if A is in the equivalence class of the identity. Yeah, again, that's an obvious thing about equivalence classes. We know that that's true, right? Two equivalence classes are equal precisely if the thing that generates the left equivalence class is in the right equivalence class, right? Okay, 3 might not have an equivalence class thing, so we're going to kind of skip 3 right now. 4 says, okay, so 4 here says that the equivalence class, maybe let me use a different color because I'm back on green. The equivalence class of A is equal to the equivalence class of B if and only if A is in the equivalence class of B. Yeah, we know that's true. Number 5 says that the equivalence classes of either, or maybe let me use words for this. So either A equals B or A intersect B is empty. Again, that's a that's a Math 102 proof. I'm certain you proved this in Math 102. And number 6 here, this isn't necessarily a property of the equivalence classes, but it's how we define the equivalence class, right? So this is actually the definition of the equivalence relation. 7 is again a Math 102 thing, i.e. all the equivalence classes have the same cardinality. All right. And then, yeah, 8 and 9, we don't have anything to say because they're not obviously related to equivalence relations. So they are actually their own things that you kind of have to remember. But now properties 1 through 7 are immediate, fairly, well, I guess not 3 either. So let me take 3 out for now. Is it obviously related? I don't think it is. Maybe I'll have to think about it more. But now these properties are just immediately the facts, come from the fact that cosets are equivalence classes, right? And so this is what I'm saying when I say, I don't remember these facts, right? Like when I look at this list of properties, I'm just like, oh yes, obviously all of these things are true because I know that these things are true for equivalence classes and equivalence relations. And that's how I internalize it. So instead of keeping 2 separate sets of information, one about cosets, one about equivalence relations, I just said, oh, look, they're secretly the same thing. And now a bunch of these things are very, very clear to me, okay? So this is worth understanding, okay? I know that this, I'm not certain if the book is going to do this eventually, like when we actually talk about quotients or not, but this is basically what's going on. And when we talk about quotients, we're basically going to define an equivalence relation on our group and then quotient out. So if you understand this idea that cosets are equivalence classes, you will be in a very good position for the next couple of weeks. Okay, it is, I think, worthwhile understanding that this is true. Okay, so are there any questions about this? Nothing? All right, well, that basically, I think, finishes this off here. So we can end class a little bit early, but of course my office hours are immediately after. So I'll hang around for the next, hour and 15 or so if anyone has any questions, and we can take them up then. Yeah, and I mean, like I said, kind of on Thursday, we're going to do the worksheet for this. Again, it's kind of worth going through and proving all of these without using the equivalence class idea, and then coming back at them and looking at them through the lens of an equivalence class. That's very useful. So you should do that. Next week, we do Lagrange's theorem, which is, again, basically what I've been telling you this whole time is that because these are equivalence classes, they partition your space. And for them to partition your space, this fact that they all have the same size, every equivalence class has the same cardinality, means and forces the fact that the order of the group has to divide, or the order of your subgroup H must divide the order of G. And basically, if you understand this equivalence class notion, you're done. Like, that's the proof of Lagrange's theorem. And is, again, super useful. If you knew this when you were doing the last assignment, question 2, where all of you were struggling with the fact that G1, G2, G49 was not in H, the order of G was not 50, show that the group was cyclic. That problem is almost immediate once you have this theorem, right? So you can see that already that it's useful. And then the week following that, we're going to actually start talking about quotients. So for the next couple of weeks, it's all going to be this stuff. So you want to make sure that you're really, really comfortable with the stuff before we actually get there. Okay. Otherwise, though, I think that's going to end it for us today. So I'm going to kill the recording. If you're not hanging around for office hours, you don't have any questions to ask, by all means, feel free to take off. And I will see you on Thursday and or next week. For those of you dropping in from Ali's lecture, it's nice seeing you. But I'm sure Ali will be back next week. And yeah, I'll see you all in a couple of days.